Last lecture, we learned about our extraordinary ability to witness directly the pre-embryonic universe, just 400,000 years after the Big Bang. By looking far away, we see the brilliant orange light from hot glowing gas, modified only by redshift of cosmic expansion, which stretches the orange light waves by a factor of 1,000. So they arrive as microwaves. It's the famous cosmic microwave background. Although we concentrated on the observed properties of the microwave background, its spectrum and its panoramic image, we also began to get a feel for the conditions at that time. Most importantly, since it was well before any stars or galaxies had formed, it was radically different from today's universe. Everywhere was simply an expanding, uniform, hot, glowing gas. If one wanted to look for parallels to traditional creation stories, some of which describe an initial era of chaos or void out of which the world formed, then here is such a parallel. Despite its utterly different form, emerging from this hot glowing gas over the eons came our current beautiful world with its life-giving sun and starry sky. Now, my aim in this lecture is to take you back to that early time, to try to experience what we might have seen or felt or even heard had we been alive back then. So let's start with a diagram that reminds us of the overall situation. Imagine a huge region today filled with galaxies. Here's the same region as it was in the early million-year-old universe. Now, there are three extremely important differences between these two regions. First, everything inside today's big cube was packed inside a tiny cube about 1,000 times smaller. This diagram, in fact, is way off in scale. Now look, here is the real difference. A 1 meter cube and a 1 millimeter cube. That's an amazing difference. That's a factor of 1 billion difference in volume. Now, second, the matter in today's cube is very clumped up. There are stars and galaxies separated by gaps. But in our smaller cube, the same matter is all smoothed out, completely uniform. And lastly, today's universe is on average extremely cold, whereas back then it was several thousand degrees everywhere. So, here are the properties we'll be looking at in the million-year-old universe: composition, density, temperature, colour, brightness, and transparency. And we'll save sound for the next lecture. So let's start with the gas's composition. Here on Earth, the atmosphere you and I are now breathing contains about 80% nitrogen and 20% oxygen in the form of molecules. So what about the primordial gas? Well, remember, about 3 minutes after the Big Bang, a brief burst of nuclear fusion produced a composition of about 75% hydrogen and 25% helium, and not much else. Now, because of the intense heat, these gases were neither atomic nor molecular. They were fully ionized. Just free electrons, protons, and helium nuclei just zooming around. Now, in addition to this, there was dark matter, outweighing the hydrogen and helium 6 to 1. But because it's so undetectable apart from its gravity, I won't look at this much in this lecture. At the same time, the same is true for neutrinos. They're present in huge numbers, but we really wouldn't have noticed them because they don't interact with anything. The other dark component, dark energy, we'll also ignore in this lecture, because back then it had a much smaller density than all the other components. Finally, there are photons, light, in enormous numbers, and as we'll see, they are hugely important. So overall, we'll be dealing with a smooth gas of electrons, Protons, helium nuclei and photons, all zooming around, bashing into one another, effectively infinite in all directions. Now, before we move on to the other properties, we need to get used to the fact that some of them will be changing as the universe expands, and it will help if we have a simple way to follow these changes in our minds. Now, the best measure of expansion is our old friend S, the scale factor or separation factor. It tracks how big the universe is. As cosmic size doubles or triples, so S doubles or triples. And remember, S is 1 today. So during the first million years, S is roughly 0.001 or 1,000th. The universe was 1,000 times smaller than it is today. Now, this graph shows how S changes over time across the first million years. It's the curve we calculated back in lecture 12. So it's 0 at the Big Bang, grows quickly at first, and then more slowly, and it passes 0.1% or 1,000th near 400,000 years. Now, if this curve S tracks the linear scale in the universe, then the cube of S tracks the volume. See, if we have a box and double its size, its volume goes up by 2 cubed or 8. Triple its size, and the volume goes up by 27. Now then, if that box contains gas, then the gas gets spread thinner throughout its increased volume. And so the gas density drops as the box gets bigger. It drops to an 1/8 and then to a 27th. So it drops in proportion to the scale factor cubed. Now this leads to a very handy formula to find the cosmic density at any time. It's just the density today divided by the scale factor at that time cubed. So, with that background, let's ask a simple question. What was the density of the gas in the young universe? Specifically, how many protons were there per cubic centimetre? That's how many protons in this cube of sugar, in the volume described by this cube of sugar, not the sugar itself. This is actually easy to figure out. Using the average density of protons in today's universe, and that's 1 per 4 cubic meters, back then, when the universe was 1,000 times smaller, those 4 cubic meters had 1,000 times 1,000 times 1,000 or 1 billion times smaller volume. So the density was 1 billion times larger, which works out to be about 250 protons per cubic centimetre. So you can see the density dropping as the universe expands on this graph, inversely proportional to S cubed. It follows this orange line, which goes with the right-hand scale, from about 10,000 protons per cubic centimetre near 50,000 years to about 100 protons per cubic centimetre near 1,000,000 years. Now that actually sounds like quite a lot, but is it really? How many molecules do you think there are per cubic centimetre in our own atmosphere right here in front of me? Well, you may be surprised to hear that there are 10 to the power 19, 1 followed by 19 zeros. That's a cubic kilometre's worth of sand grains. So cosmically speaking, we live in an exceedingly dense environment. And the primordial atmosphere is incredibly rarefied by human standards. In fact, it's more rarefied than the best vacuum that scientists can make on Earth. So does the primordial atmosphere ever equal our own atmospheric density? The answer is it does, but only 10 seconds after the Big Bang. So after only a few minutes, the universe's density of protons and electrons is much lower than anything here on Earth. Let's now consider the temperature during the first million years. Remember that the young universe was very hot, but it cooled as it expanded, following this curve. At 50,000 years, it was 10,000 degrees. At 400,000 years, it was 3,000 degrees. And by 1,000,000 years, it was 1,800 kelvins. That's 1,500 centigrade. It's about the melting point of iron. Now, here's a question. Sitting in this gas at several thousand degrees, would it burn you? Surprisingly, the answer is no, it wouldn't. It's far too thin. Remember the heat is associated with the jostling motion down in the atomic world. And the heat energy entering your skin, which determines whether you'd be burned or not, depends on two things: the average kinetic energy of each particle and the number of particles striking your skin per second. Now, in the early universe, even though the kinetic energy of the particles is high, because the gas is hot, there are so few of them hitting you that you'd barely even notice their heat at all. However, despite surviving the hot gas, light would kill you instantly. So let's turn now to look at the primordial light. At various points in these lectures, I've commented that the young universe was very bright. A big flash might be a better term than a big bang. And why was this? Why was there so much light created? The simple answer is that the universe was born hot, and hot things glow, just like this piece of iron or this furnace. In Lecture 4, I mentioned why this happens. When two charged particles collide, like an electron and a proton, the collision creates a photon of light. Now, as long as the particles and photons interact and share their energy back and forth, they both arrive at what physicists call thermodynamic equilibrium. Essentially, all particles have the same broad spectrum of energies and therefore have the same temperature. Photons, for example, have a thermal spectrum like this, a broad range of colors with a peak. As you can see from these other examples, at lower temperatures, the thermal spectra are weaker and with longer, that's redder, peak wavelengths. Now we can understand why the universe cools as it expands. Two things happen. The expansion causes all the photons to be redshifted to longer wavelengths, and they get more spread out. They're diluted. And together, these yield a weaker, redder spectrum, which is another thermal spectrum, but with a lower temperature. Bingo! Cosmic expansion, with its redshift and dilution of photons, has just cooled the universe. Let's be slightly more quantitative. If we double the cosmic size, the wavelength of all photons also doubles, and so the wavelength of the peak of the thermal spectrum doubles, and this corresponds to half the original temperature. So we have a very important relation. The cosmic temperature is inversely proportional to S, the scale factor. And it's this relation that gave our graph of cosmic temperature across the first 1,000,000 years. Okay, so now let's return to the simple question of what would we witness in the young universe? Floating there, looking out into the distance, what would we see? Well, since light comes from every direction, you would see this extremely uniform glow all around you, rather like a 360-degree panoramic bright sky. Now, because the light has a thermal spectrum, this leads to a rather stunning spectacle. As the universe cools, the whole spectrum shifts to the red, so the sky color changes. Here's what happens over the first 1,000,000 years. Starting at 50,000 years, the sky is blue. At 200,000 years, it's yellow. At 400,000 years, it's orange, and by 1,000,000 years, it's crimson. The universe's sky color slips through the rainbow sequence backwards, spending roughly 80,000 years in each colour. This is a wonderful and beautiful quality of the young universe. It actually paints the sky with a palette of human colours. Now, although we'd recognise the colour of the primordial sky, how bright would it be? I mean, could we stare at it without squinting? I'm afraid the answer is a very definite no. Not only could you not stare at the sky, nor would it just blind you. It would incinerate you almost instantly. For example, around 100,000 years, the temperature was about 6,000 degrees, which is similar to the sun's surface temperature. So sunlight gives us a good idea of what 6,000 degree thermal emission looks like. So the primordial sky glows from every direction with an intensity and colour similar to the sun. You see, it's as if you're standing on the Earth, not with just one sun in the sky, but 210,000 suns, a sky filled with suns, no gaps between them. This is what the young universe was like. When I said it was fantastically bright, I really wasn't exaggerating. Now, another way to experience this would be to dive down 1,000 miles into the sun's atmosphere. You'd be surrounded by a brilliant glowing gas. The light alone is powerful enough to evaporate you in 10 seconds. Here's a plot which shows all this. It uses the same line as the falling temperature, but it uses the right-hand scale to follow the sky brightness in noontime sun equivalents. So going backwards in time, starting at 1 million years, one sees a panoramic, featureless, crimson sky as bright as 1,000 suns. By 500,000 years, it's now deep orange and as bright as 10,000 suns. At earlier and earlier times, the brightness soars upwards while the sky colour sweeps through the rainbow sequence. It's an utterly fabulous, if lethal, spectacle. So why does the primordial light have such awesome intensity? As usual, it's due to expansion and redshift. So let's imagine going backwards in time, halving the scale factor. So volume gets smaller by a factor of 8. So the number density of photons goes up by 8. But each photon's wavelength halves. So its energy goes up by a factor of 2. So combining these, the energy density of light increases by 16, which is a really big increase for just halving the cosmic size. We've actually come across this in lecture 12 already, when we saw that unlike matter, whose density changes with the third power of the scale factor, the density of radiation changes with the fourth power. That extra power comes from redshift. Now, the fourth power is the square of a square, which means that light's intensity is extremely sensitive to the scale factor. So going backwards to earlier times, light's intensity increases incredibly fast. For example, when the universe was 1,000 times smaller than today, the intensity of light was 1,000 to the fourth power. That's 1,000 billion times higher than it is today. Well, if you take the microwave background and boost its intensity by 1,000 billion, that's enough to kill you instantly. So far I've emphasised how brilliant the light is and how rarefied the gas is. But let's be more specific. What's the relative number of photons to protons? What's the photon to proton ratio? Well, in today's universe, it's just the ratio of the photon density in the microwave background, which is 410 per cubic centimetre, to the density of protons, which is 1 per 4 cubic metres. That makes a ratio of 1.6 billion photons for every proton. It's a huge number. Now, it turns out that that number doesn't change much as the universe expands. So the photon to proton ratio is approximately fixed and it's an important parameter for our universe, and it was set somehow in the first second of the Big Bang. Now, in Lecture 29, we'll explore why this number is so big. But for now, let's just register the fact that photons are enormously numerous, more numerous than protons or electrons, by about a factor of 1 billion. So imagine a cubic meter filled with sand. Let me take 60 grains of salt and throw them in. Those would be the protons compared to the photons. So cosmically speaking, matter particles are extremely rare compared to photons. Now, but although that's true for the universe as a whole, here on Earth, the situation is completely the opposite. We live in an enormously matter-dominated environment. Even under a noonday sun, our atmosphere contains 100 billion molecules of air for every solar photon. Now, having stressed light's huge abundance in the universe, it's important to ask whether it also contributes to the gravitational field. Remember that energy and mass are deep down the same thing, E equals mc squared. And so any source of energy, when divided by c squared, gives a mass that in turn generates gravity. So a very important question is, for the million-year-old universe, which has more mass, matter, or light? As you may remember from earlier lectures, the answer to this question changes with time. As you can see in this figure from Lecture 4, which shows how the density of the major cosmic components changes as the universe expands, from left to right. Both axes are exponential, so it turns out that the densities follow straight lines. So remember then, dark energy is constant. So although it dominates today, it was irrelevant in the early universe. Now the other two lines are for radiation, which includes neutrinos, and matter, that's both atomic and dark. And both these increase rapidly going towards earlier times, simply because the universe was smaller. But notice that the line for radiation is steeper. That's because it's increasing with scale factor to the 4th power, while matter's density only increases with scale factor to the 3rd power. So although radiation starts out today much less important than matter, the two lines cross when the universe was 5,000 times smaller than it is today. That's roughly 60,000 years after the Big Bang. And at that time, radiation and matter densities were equal. And of course, this separates the two great cosmological eras, the radiation era and the matter era. Now, ultimately, what's happened is that at earlier times, the blue shift of each photon boosts its energy, and this gives light the advantage, and it guarantees a radiation-dominated early universe. Here's one example I've used before. At about 10 seconds after the Big Bang, the proton density roughly matches our atmospheric density. But light was 200 times denser than lead. What an amazing situation. Now, you may worry that this is all too theoretical and impossible to verify, but that is not so. In Lecture 17, we'll discover that this crucial transition, near 60,000 years, when light yields its gravitational authority to matter, leaves its stamp on the pattern of galaxies across the sky. Essentially, it defines the boundary about 200 million light-years that separates small-scale inhomogeneity from large-scale homogeneity. But let's leave that topic to Lecture 17 and move on. So the last property I want to talk about is whether the young universe was foggy or transparent. Stated simply, could you see your hand in front of your face? Now, to answer that question, we need to know what causes fogginess. In the case of a terrestrial fog, photons deflect off tiny water droplets, so they don't travel very far in straight lines. They scatter around randomly like a pinball, diffusing haphazardly through the fog. Now, what might cause photons to scatter in the early universe, causing it to be foggy? Certainly, there were no water droplets. It turns out that free electrons scatter light. They're lightweight charges that wiggle when a photon passes by, causing it to be deflected. The process is called Thomson scattering, after J.J. Thomson, who discovered the electron in 1897. Back to the young universe. With only a few thousand electrons per cubic centimetre, the fog is extremely thin by human standards. For example, after 100,000 years, the fog's visibility distance was about 500 light years. Now, as the universe expands and the density drops, this visibility distance increases, like the blue dashed line on this plot. At earlier times, the visibility distance gets much shorter. But only about 1 second after the Big Bang could you literally not see your hand in front of your face. A rather moot example, since at that time you'd evaporate in much less than a nanosecond. Well, since there were no people then, arm's length is hardly a relevant distance. But what is relevant is the horizon distance. Remember from Lecture 8 that the distance light travels since the Big Bang is called the horizon. It's as far as you can possibly see. At 100 years, it's roughly 100 light years, the age of the universe times the speed of light. So here's a question. Can you see to the horizon? If you can, then the universe is effectively transparent. If not, then it's effectively foggy. Well, here is the horizon distance. It's basically the cosmic age in light years, and it curves this funny way because the y-axis is exponential, but the x-axis is linear. At 100,000 years, for example, the visibility distance of 500 light years is less than 1% of the horizon distance. And that's equivalent to just 30 yards visibility if you were standing on the seashore. So it is definitely foggy. But as time passes and the gas thins, you can see a larger and larger percentage to the horizon. If we extend these lines, they'd cross near 45 million years, and you could finally see to the horizon. However, well before that, near 400,000 years, a dramatic event occurs, which makes the visibility distance do this. If you remove the water droplets, the fog clears. In this case, the free electrons are removed. They're caught by the protons to make atoms, and so the fog quickly clears. Cosmologists call this recombination, and it marks an amazing transition from ionized to atomic, from foggy to transparent, from sound to silence, and from smoothness to roughness. It's one of the most important changes in the entire history of the universe. So let's briefly look at what happens. As you know, the early universe was far too hot for atoms to form. Collisions by particles and photons just bash them apart as soon as they form. But as the universe cooled, by about 400,000 years, the conditions were calm enough for electrons to be caught and held by the protons, and there was a frenzy of pairing up. The transition took about 80,000 years to complete, but after that, the gas contained neutral atoms of hydrogen and helium, which is quite a different kind of gas. Now, this atomic gas was completely transparent to the deep orange light that was present in the universe at that time. So, from then on, the photons were free to stream without interruption in straight lines as far as they could go. Almost all of them are still going, unchanged, except by redshift, though a very few do end their long 14 billion year journey rather abruptly when they run into your head as a microwave background photon. That, of course, is what the microwave background is. It's our direct view of that time. The light has come to us uninterrupted across a transparent universe. The last time that photon was scattered was back in the 400,000-year-old universe. In fact, cosmologists sometimes call the microwave background the surface of last scattering. Let me end this lecture by looking a little differently at this topic. In our astronomer's view of the universe, we are surrounded by a 3,000-degree glowing gas. Now, in a static, non-expanding universe, its great distance wouldn't diminish its intensity. Remember from Lecture 8, surface brightness is independent of distance. Naively, then, we should see a sky covered by 3,000-degree suns. We will be at the center of an utterly lethal oven with 18 megawatts of power falling per square meter. Now, what saves us is cosmic expansion, which transforms this brilliance into an imperceptibly feeble microwave background. Remember also from Lecture 8, in an expanding universe, the surface brightness decreases with the fourth power of the scale factor, so that when the oven walls are redshifted by a factor of 1,000, the oven's brightness is reduced by a factor of 10 to the 12. That oven of 18 megawatts per square meter becomes a refrigerator of 18 microwatts per square meter. It's the 3-degree Kelvin microwave background. So who would have thought that redshift alone would save us all from a fiery incineration by the cauldron of creation?